Morning, everyone. Let's start. So long, I see there's still a couple of people joining, but the first couple of slides are the brief overview of what we did in the last session. So this is just, again, the topics that we intend to cover. We've already done this. I'll just keep on using the same slides so that you have an idea where we're going to. So the contact algorithms, basics, contact of Nastran and Marc, so on. What we have covered so far is the sections in blue. We started on contact interactions and some other settings inside of the contact table, but this is what we'll spend today discussing. Okay, let's just briefly recap on what we did in the last section. We spoke about the contact table and why we want to use it. And the idea is if you don't use a contact table, then all your contact bodies automatically can touch each other, but everything will be default settings. Touching contact only, you have no control over certain behavior for different parts. So in a contact table, we can change stuff like whether it's touching or glued contact, some interference fits, and. So a lot of that is what we'll actually spend today on is what exactly are those options that we have available in order to, or what is changed effectively in the contact table. Okay, so another thing we spoke about is to try and use fewer contact bodies. If you just say automatically detect every mesh that's not connected to other elements will be treated as a separate one, and we'll end up with a massive set of contact bodies. So the idea would be try and lump stuff together that vaguely makes sense. An example that we've used in the previous one, all the washers and all of the bolts was each added to a separate contact body, instead of having a separate contact body for every bolt. So this makes it a lot simpler to set up contact tables and a lot less chances for mistakes. So yes, you can still make mistakes, but a lot easier to make a mistake if you have a massive contact table. The contact interaction is something that we use in the contact table, and the purpose of that is it's a reusable component. So it's something that we want to set for lots of bodies. So for those body pairs, we can set one contact interaction, define the settings, and I can keep on reusing it instead of changing the settings for every specific part. So this is what we'll talk about in this section. If I open the contact interaction, for the touching contact, this is what I see. I mark the first one in blue because the first two, contact tolerance and the bias, we've already spoken about. But this is where we can override it. In other words, you override the global settings. So this is where we specify it for specific pairs of bodies. So the ones in white are the section that we'll discuss now. Now let's just show you the glued contact, similar. So the first couple kind of look the same. And there's a couple of additional options at the bottom. By the way, there in the middle is where we set contact type, touching or glued. Okay, so this is if I add both the touching and glued interaction. These are the list of properties that's the same between touching and glued contact. So in other words, the tangential extension, that option over there is available for both, and also that option for stress-free projection. It's available for both. So when I discuss these, I'm discussing it for both. It doesn't matter whether it's touching or glued. It has exactly the same effect and the same purpose. So let's first talk about tangential extension. So this is a model, whether it is due to loads or so on, or bad meshing initially. If I zoom in, just go back in that little bit over there, I see, and I have to zoom really far, I see that the blue part slightly overlaps the red part. So what that means is on this side, assuming it doesn't overlap, if I make contact from the node on the blue to the red, it's well defined. That node will be able to touch. But what should happen to that node there? If I use a perfect mathematical correct contact model, it will simply fall off. And that's not what is really going to happen, because actually that whole face is touching, except this last bit. Okay, so and that's the purpose of the tangential extension. And there I've done it, and you can actually see the effect. I've just visually drawn it in. It's not clear there, so let's zoom in. What it does is it says, well, if I look at contact from the top to the bottom, so the blue nodes to the red faces, in all of those locations, I've got them making contact on this face. So that last one, let's see what happens if you just extend that by about 10% of that edge length. That's the default. You can change the value. But that says that blue node will now make contact on that extension of that edge, meaning the load will be transferred to those nodes. Okay, so typically what happens if this was, let's say, a rubber part, I apply a load, and due to that, this expands sideways and these start falling off, and you start running into these kinds of issues. So as you can see, it's again a perfect contact algorithm that doesn't really exist, that automatically does everything. There's always these little exceptions that you have to take into consideration. And this is the purpose of this is to try and look at those. Okay. The second one is stress-free projection. So if I have a mesh like this, it looks good, and I start zooming in, I say, oops, there's a bit of an overlap. That can be due to bad CAD. It can be that there should have been an interference fit. So the question is, what will happen if I run this model? Let's say I constrain this on the top and the bottom, and I run this. These nodes will be moved back onto that face, and due to that, there will be a compressive stress in this direction. If that's what you wanted to model, perfect. In other words, if the intent was an interference fit, great. But if this was bad CAD, bad meshing, any of those, and in some cases not so much bad meshing, but if this was at an angle, round-off error can actually cause this kind of behavior as well, where some nodes penetrate, some doesn't. And you look at that same, I constrain it there, and I see pretty interesting stress distribution that really does not make sense. I've seen models where I glue something like the blue part to the red, and I see a 2 gigapascal stress initially just due to that initial contact. It's a little bit of overlap here and there. So whatever loads I then apply just disappear in terms of that massive stress that I see. So what the option will do, the stress-free projection will say, if there is an overlap like this, it'll move that node perfectly to where it should have been, but it defines the initial mesh as starting there instead of this little bit of an overlap. In other words, it's doing a bit of cleanup on the mesh before the run starts. So that new location is the actual initial location that you see in your model, or how it's treated. Okay, so to do the first, you activate that tick box. To do the second, you activate this one. So the first one you do whenever you have a block standing on top of a block, so edges that's really close together, you're not certain whether it may fall off during the run, you can activate this one. The second one is when something initially should make contact but not have a stress, you can activate that section. The other options that are now only available on touching but not on glued are these bottom ones. So friction, wear, and separation. Now, by the way, there's a section there on augmentation. These settings has to do with the segment-to-segment method. So I'll treat these specifically once we talk about segment-to-segment. Okay, so if I look at the three, so we've got the friction coefficient. If I specify friction, I can specify the friction coefficient. But why is it defined here and not on the contact body itself? Why don't I say steel as a friction coefficient of randomly, let's say 0.1 or 0.3 or whatever? And the reason is friction is a function of two body pairs, a material touching a different material, so it's a function of the material pair in contact, and it's also a function of the surface finish of both parts. So if I look at the first one, if I have Teflon on steel is arguments like around 0.01, but Teflon on Teflon is also about the same, 0.01. But if I look at steel on steel, that may be 0.1 or 0.3 or whatever, depending on the surface finish. So there's no way to specify on the contact body that would make sense. So the interaction, because I'm going to reuse it, let's say I've got a model with different materials in steel, aluminium, plastic, I don't care. Then I specify an interaction, and I can give it a name that says this is specific to touching between steel and aluminium parts, and you fill in all the properties. The second one is wear. Now, on the contact body itself, we actually specify the wear parameters and the wear model and so on. So the coefficients that you need. In here, we only have a scale factor. So we typically use this if you run, let's say your run takes 1 second, but the actual behavior is over 1,000 seconds, you can then say scale it up by 1,000 so you can see what the effect is of a longer duration. So you're just scaling the wear rate effectively in this section. And the last one is separation. So bear in mind this is touching contact. So touching contact says if I apply a tensile load, it should separate, or that's the theory. But in practice, what happens if that tensile load is 1 nanonewton? Should it separate or not? And the answer is I don't really care. Whether it's in contact or not, actually the machining tolerances will be worse than that, so it may actually be in contact or not, but it's not going to change the answers. So the contact algorithm will allow a little bit of a tensile force before it separates, and there you can specify what that will be. So you can manually specify it. But what's the default value? The default says, let's look at the maximum residual. That's just Marc terminology for the maximum unbalanced load anywhere in the model. And you say we'll allow that same force. So that says, if I look at a node and the total force on that node, and by that I mean both external and internal, is not 0, I get a value of 1 Newton argument. So I then also allow a 1 Newton tensile load for contact. Now, why is that important? There should be perfectly 0 unbalanced load at every node in your model. But since they're not, it's a nonlinear analysis and we need iterations to converge. Effectively, the tighter your tolerances, the smaller tensile load it will allow. So this results in a model that actually behaves well. If you try and force it to a specific force value, you'll run into different issues. Let's say you specify arguments like 1 Newton or 1 MPa or 1 Pascal or whatever for separation force or stress. What will often happen is that initially there's not much load, so that load that you're specifying for separation is actually really large relative to the loads you're applying, but later on it's actually really small compared to everything else. So it doesn't scale with the loads in the model, while the default does scale with both loads and your convergence settings. So these are the only additional settings that we can specify. So in summary, touching contact, we can override the tolerances and the bias. We can extend the edges a little bit if needed. We can specify stress-free projection, and then we can change friction, wear, and separation. The ones that we'll use the most will be this one for specific models where we have in that example that it looks like it's a corner touching a corner. We'll do that. But this one we also use a lot, stress-free projection. In most models, we want to start in a no stress condition. Even if it's interference fit, I'll still do that. There's a much cleaner, easier way to perform an interference fit. If I now look at the glue one, so again, we have that same settings. But now if I change the glue, I've got a glue model. So the standard model says it's infinitely stiff. If I open that drop-down list, the other option there is a cohesive. And that is if you really want to model an actual glue kind of connection. So you've got 2 parts and there's some kind of epoxy or something in between, but you don't want to model that using elements. So in this case, you can define stiffness of the glue in the different directions. You can even define failure for that. Then this middle section, if I look at shells, if I look at the normal contact algorithm, it simply said the node cannot penetrate or separate from a face. But that's translations. This option simply says, but for shells, we also want, if I really want to glue, I should actually include moments. But there it gives you the option, do you want to include that effect or not? So the default is actually to have it on. In most cases, that makes the most sense, but you have the option of switching it off. Okay, touching contact doesn't really matter because we're in the glued interface. Okay. So next one is if I look at the remove gaps and overlaps. What this says, if I go back to, yeah, there's going to be a couple of slides back. Okay, so that example that I had where we project stress-free, in other words, there was this little bit of an overlap. I can also say, but either remove it. If I combine these two, in other words, I switch this one on and remove it, the nodes will be moved back perfectly onto the face, and that's the stress-free state. if I have this off, but this still remove gaps, then we'll move the node to the face, but that'll cause a stress, which is probably then what you wanted. But we also have the option of saying, I want to retain the gaps and the overlaps, still glue it in that location. So in other words, effectively the same happens if I do that with this off as with this on, and that set to remove the overlaps. In other words, it'll glue the node slightly below the surface or above the surface, depending on where it started, but it'll pretend there's material in between. So why on earth would I want to do something like that? And the reason is simply because I'm not moving the node, I'm not distorting the element in addition to anything else, in addition to the loads that I'm applying. This is something that you often see with second order elements. You start projecting or moving those nodes onto the face, and then suddenly the model doesn't want to run because it said some elements are inverted or something. So it's just an alternative method. In terms of the results, it should be nearly identical. I say nearly because that little bit of overlap that we're retaining effectively removes a little bit of material, but that's it. Okay, so the next section is separation. So we can allow separation, but if you look at this, there's separation and there's breaking glue, which is, well, it sounds like it's separating. And the two are similar. Okay, so for the separation, we can specify force or stress limits for that contact, but let's say it's separated. In other words, I specify at 1 kilonewton, these nodes should separate, but if they come back together, it'll glue again. So it's kind of like Velcro. Pretty large force, you need to separate them, it just needs to touch and it's stuck again. Okay, so I can't think of too many materials like that unless we're wanting to model some really simplified magnetic contact. Okay, the second option is breaking glue, which is very similar. We specify stress limits, but what happens is once it's broken, if it comes into contact again, it now uses touching contact for the nodes that used to be glued but has broken. Okay, so this is a bit more physical. So you can use this to, let's say, separate when you exceed the strength of the resin that you're using, the epoxy or the whatever glue you're actually using. But then if the load is in the opposite direction, it will touch. Otherwise, if you don't have that, it'll simply push through. Okay. That's the glue settings. Okay, then there's a couple of additional settings on the contact table. So if I look at the contact table again between two bodies, doesn't matter which bodies they are, we have the interaction set there, and that we can use for lots and lots of bodies. Now, here's a couple of really important settings. So the first one is the contact detection method. Now, I have to specify that this is only used for node to segment. But open that list, you'll see there's default, automatic, first to second, second to first, double-sided, and so on. So I've tried to color code this to make it hopefully a bit easier to read what's happening. Okay, so as I say, it's used for node to segment. So what it says is, if I have first to second, I mean the first body's nodes is checked against the faces of the second body. So their nodes in red, that's the, not the word first, it's the first one, nodes to faces. Okay, and the faces in green. So if I use first to second, it says the first one's node, it's touching the second one's faces. The second option there would be the second one's nodes would touch the first one's faces. Now, why do I start with this? These are the only two options kind of that happens in the background. Everything else is related to these two. So the default would be whatever is defined in the job. So in your job, there can be any of these, first to second, second to first, double-sided, automatic, whatever. But if I use default, it'll use whatever is defined on your job settings for the contact. The second option is to use automatic. Now, we previously mentioned that ideally I want to let the finer mesh touch the coarser one. Otherwise, especially if it's significantly finer, then it's critically important. If it's slightly finer, it doesn't matter too much. So the finer mesh should touch the coarser mesh. In other words, the finer mesh's nodes should touch the faces of the coarser mesh. But the second requirement or second ideal would be if the lower stiffness material touches the higher stiffness material. In other words, if I have rubber and steel, the rubber should touch the steel, not the steel the rubber. Again, it just improves the contact behavior and so on. Not a massive difference, but still it's important that material plays a role. Now, the question then is, and there is that weird number there, a hard-soft ratio, is if in the automatic method, it'll pick it based on these. So it'll try to use the finer mesh as the first, the nodes part, and the coarser one the second, but it will also look at material stiffness. And this hard-soft ratio says if the elastic modulus or the stiffness of the two parts are more than twice for the second one than for the first or something, it'll base it on material stiffness. In other words, if you look at the steel and aluminium, so steel is around 200 gigapascal, aluminium around 70. So that ratio is just below 3. So in that case, you'll look at material instead of mesh density. So that's for the automatic method. Okay, so if you want to use the automatic, it's really not a good idea to have a fine mesh being touched by the coarse. In other words, the coarser one touching the fine. So if you have this, let's say aluminum and steel, rubber and steel, try to make the lower stiffness the finer mesh as well to ensure that both of these are satisfied. Otherwise, at the end, when you try to run the analysis, you will probably, or quite likely at least, run into issues. And the last option is double-sided. This will say first check the first nodes against, or first body's nodes against the second, and then the second against the first. Now, I keep on talking about first and second. It's simply the sequence in which is listed in the contact table. So I'll tell you for this body pair, the first is contact body 1 and the second is contact body 2. I could have named them whatever I wanted, but what first to second would mean is body 1's nodes would touch body 2's faces. Second to first would be the opposite. Okay, then getting back to the last option is double-sided. So is first check the first body, in other words, that body against this one, and then check it in reverse as well. And at first glance, that sounds like a good idea. In practice, it's not. So especially if your first body is the coarser mesh, then I'll take the nose of the first, check it against the second, and then reverse. But then what you typically find is there's some nodes that should have made contact, but due to circular dependencies in the equations and so on, it's not possible. So some nodes will be missed. Even worse, if I look at the contact status, instead of seeing on the one body this nice contact patch where it's touching, you will see it in some nodes on the one face and some on the other, and it's really difficult to figure out what the actual contact face is. Now this, as I say, is only a node to segment idea and a method. Once I look at segment to segment, it's not making contact at the nodes, it's making contact at lots of internal locations. But that's a topic for a different section. So what would I recommend? Well, what I almost without exception do is I manually define these. So each body pair, I look at the mesh for the pair and decide for that pair, should it be first to second or second to first? And one of the reasons for that is sometimes you get to this point and you realize, okay, but I've got both fine mesh, but also the lower stiffness on the other part. And that shouldn't work. So then you can immediately go back and try and fix that. But still, by doing this, you can ensure that what you expect the model to do actually happens. So I just have a lot less issues if I manually define all of these. So, okay, then in terms of the contact table, there's a couple of additional settings. If I look at these two, the boundary redefinition, I can change, and this has to do almost without exception to do with shells, whether it's first or second body, I don't really care. It's so the first and the second simply again refers to these first and second. If both of those were shells, and let's say in some parts of the model I want to make contact on the outside faces, and some I want to make contact on the mid faces, or I want to make contact on top on some faces but on bottom on others. this is where I redefine. I say for this specific body pair, take the first body and change the default settings. So the default settings is defined on your job again. So the defaults for shells would be make contact on the top and the bottom faces, but take the thickness into consideration. So if you've meshed differently, you can change it there to say top or bottom, and then you can ignore thickness, but you can't over there say top and bottom and ignore thickness. We've discussed that two sections so 2 months ago. Now, in this case, let's say there's a certain shell, let's say body 1 for body 2 makes contact on the top, but on body 3, it should be the bottom. Because it's different pairs, I can then, for those, specify the first body should be ignore thickness and top only for the one pair, and in the second one, I can change it to the opposite. Then the last two I want to briefly mention. This last soft I've actually spoken about because it has to do with that. Initial gaps and overlaps or interference fit. Both of those have very similar intent, slightly different application in or exactly how it works. The easier to understand and use is interference fit. The initial gap and overlap is slightly more specialized. So the intent of the interference fit is, there's a couple of methods, but there's two that you use a lot. The one is physically modeling an interference fit. I've got a pin in a hole, but due to roundup error and so on, I can't overlap the meshes by a micron or 2 microns and get good results. So what we'll do is we'll rather project stress-free initially. But then we ramp up an interference fit. So when you ramp up that interference fit, you're actually forcing the one side to make contact with the other slightly before it actually touches. So what you'll physically see is a gap seeming to open up between the two. But if you look at the results, there's a contact status. So in other words, that knows after one body is in contact with the other one, and it causes stresses because effectively it makes contact before the other part. Said another way, one way of looking at it would be to say we're effectively forcing a shim in between these two, but we're not seeing the shim. So that's why there seems to be a gap. It's still in contact, it still causes stresses. It just opens that little bit of a gap. So what's the advantage of that? It's a lot easier to get really good answers for interference with using this method when I compare it to the mesh overlap method. On simple shell models and planar models, it's still possible to do the overlap method. I think one of the Marc standard examples actually does that, but try to do that on a solid mesh with meshes that don't tie up and so on. It's nearly impossible to get right. But as I say, doing it like this is actually really easy to do. Okay, the second one has to do with rubber seal insertion. So if you look at an O-ring in some kind of a section, if you take the O-ring out and then you clamp it closed, there where the O-ring would have fitted, and then magically you try and fit the O-ring back, you'll see that the O-ring overlaps with the material above and below it as expected. But what will happen now is using that method, we'll say, okay, allow a lot of interference initially, but we'll define that temporarily as the zero stress state. And that overlap that it allows will be reduced over one load case to the point where that O-ring is forced into the right shape. But, so it's not that easy to understand if I don't have a visual example. Unfortunately, I don't have one close by, but it's more something to take into consideration. Just remember, if you need to do this, just talk to me and I'll show you how to do it. It's really, really simple to set up. Okay, so that's it in terms of this. If I look at the contact table between two bodies, I've got the interaction. I've got the method. Should it be first to second or second to first or whatever method? Do I need to redefine where the shells can make contact or not? And do I have interference fit? So let's look at a simple example. This is the exact same model I had in the previous session. But let's start talking about what settings we'd need ideally for the different locations. Okay, so let's start over there on the right. So that, let's say the lug in this plate section. If it was an interference fit that I need to model, what settings would I need to run? Which options would I need to use? Okay, so ideally project stress-free to start off with, but then also the interference fit that'll ramp up to then cause a stress in that location. I'll also need friction, because without friction, this thing will simply slide out. But that's it, not much else. I don't need to model that, use that delayed slide off, since it's touching contact also. None of the other separation stuff is important. If I look at these sections, for example, so let's say the washer to the plate, I'll just use project stress free, because chances of an overlap occurring is reasonable, not necessarily always, but in a lot of models we'll have that. So by using that, it'll move those nodes as needed perfectly onto that face, and the contact starts. If I look at the washer to this L bracket, in which direction should I make contact? From the blue to the red, or from the red to the blue? Okay, assume they're both steel. If it's both steel, then obviously from the blue to the red. Why do I say obviously? It's got the finer mesh. So the finer mesh will always touch the coarser mesh. Now this is actually a bad mesh, to be honest, because for other reasons I may want to make contact from the green to the blue, simply based on I've got a really well-defined outline where the nut touches the washer. But as you can see, the mesh on that is a lot worse than the mesh on the washer. So in this case, if I want to use this mesh as is, I'll be forced to use from the washer to the nut. Okay. Ideally, I'd like to remesh this because I want to make contact from the green part of the nut to the washer, simply because the nose there on the outline exactly determines where the interface or the outside edges of that section is. It's not going to make a massive difference, to be honest, unless I've got a really coarse mesh on both of these sections. What about this section, the bolt itself, that shank section, and the nut, or the threaded section in there? I'm not modeling the thread. I'm probably going to use glued contact between the two. There's lots of different ways of preloading this. One method would simply be I apply a force vertically down on the top face of the nut and a tensile force there to preload it, but I use contact between these two. And then in the second load case, second contact table, I say, okay, now I've got that preload on, now glue these two, and then I release the force. So that's one way. There's lots of other ways as well. Okay, but again, I'll use project stress free because I don't want a radial stress at the bolt, between the bolt and the nut. And I want it perfectly in contact. So what I'll do is I'll run the analysis without even a load case with that contact table and check that it makes contact nicely. So which mesh is finer between these two parts? That's a lot harder to say. You'll have to zoom in a bit. It's not that clear. I think the green is slightly finer on that interface than the nut. Sorry, the nut compared to the shaft. So in that case, I'll again, assuming this is slightly finer than that, I'll make contact from this one to that, depending on, so if I look at the sequence there, this will be the first and the second body, simply because that's the order it lists them. So I want first to second if this one is the final mesh.
Gerrit, you've got a question from Mangalani.
I can't see the question,
No,
unfortunately.
he raised his hand.
You're welcome to ask.
Okay, thanks, Gerrit. I just want to find out, now that you were mentioning about the contact between the nut and the bolt, how would you go about specifying the contact between the cylindrical contact between the washer and the bolt? Would you have to specify that as well, since you did it for the bolt and the nut? Do you have to do a specified concentric contact between the washer and the bolt as well?
Okay, so there's no such thing as concentric, but it's a geometric concept. So
Yeah.
on that way, you're welcome to either define contact between the blue part and the pink, in other words, the washers and the bolts, but you probably won't need to if you're on friction, because that's one
Okay.
thing that's also important here is you'll either run friction between the washer and the L brackets and the nut and the washer, and if that's contact, fine. Otherwise, again, at the bottom, we'll have the head and the washer and so on. So you'll either run friction between these parts, or you simply glue the washer onto this.
Okay.
So the assumption for this joint would then be, due to that load, if I preload this and I pull on this, the load will go from this side through the nut, sorry, through the bolt, through the nut, through the washer into this, and is in friction being transferred. But
Okay.
if for whatever reason it slips enough so that that can make contact, you have to have that in.
Okay. And then thanks, Gerrit. And then maybe the last one, I just want to find out if there is a way that you can determine, let's take for instance, now it's difficult to see which one has the finer mesh between the bolt and the nut. Is there a way where you can see maybe the number of elements that can tell you which one has a lot of elements that would be used to determine which one has a finer mesh or not?
It's actually easy to find the number of elements, but that doesn't tell you much because a larger part with larger elements can have the same number of elements. So what you rather do
Okay.
is you simply measure between nodes. So you use the
Okay.
measure tool. So I'll measure from there to there, argument's sake, those two, and then I'll measure those two nodes. And I'll compare the distance.
Okay, it's clear. Thanks, Gerrit.
Okay, the last one that we haven't discussed was simply the yellow part of the L bracket, so the center plate. And there's nothing special we need there other than, again, stress-free projection, which I almost always use. I don't want an initial interference slip there. And I need to specify friction between these two if I want to run include friction effectively. If I don't include friction, the model will actually not run because it's effectively as if I then have Teflon or grease between the yellow and the L bracket. So in that case, any load that you apply, this will slide around and it's going to be difficult to get a static solution. In a transient analysis, it would be easy, but not in a static one. But again, it's not physical. So that's why you'll either run friction between these parts or you'll just glue them together. To be honest, I'll think very carefully about gluing these, but over there I may still consider gluing the washers and the bolts, washer nut and the plate together. But again, you can use friction as well. So that's it in terms of how you look at the model. You look at each joint and determine which settings are needed and why. And based on that, you simply use an interaction that makes sense and add additional settings if anything additional is needed. Okay, so that brings us to the end of the section. We looked at the contact interactions and other settings on the contact table in this. Next section, we'll start looking at node to segment. Depending on how much detail we add, we may actually start with the segment to segment stuff as well. Okay, so what we'll do towards the end will be specific models to show how interference work. We'll also spend time on friction models, stick slip and bilinear and all of these methods and so on as well. So while all of them actually has to do a little bit with the contact table and some of it we've mentioned, it's easier to show specific models and treat each of those as a separate model than in a separate section and trying to do everything here. Okay, so that brings us to the end of this session. Thank you for joining. Any other questions?
Sorry, Dave. Yeah, I had one question with regards to glued contact. You mentioned stress. Generally, stress is related to strain, but what about strain? Because some glues, if they move at all, they break.
To be honest, I don't think there's anything that exists like saying if it moves at all. So a little bit of strain will also always be visible and so on because there's an elastic modulus. It may move very little or very low strain before it fails, but there is still a strain. So you can define that argument's sake as a 1e minus 6 strain or something weird.
Okay, so you still have to go back to stress and then, okay, understood.
I think that specific method is only stress-based, but I know there's some stuff where you can also fail based on strain. Or change behavior based on strain instead of stress. I'll double check whether it's available for the contact as well.
Okay. All right, perfect.
Just on that, Dave, if let's say you've got a strength value for the resin or the glue, and you're not too certain about stiffnesses, what you can just as well do is glue it as if it was perfectly glued, and then just separate based on the normal stresses and the shear stresses,
Okay.
instead of using the cohesive elements where you specify stiffnesses in addition. But you tend to get more accurate stresses in stress distributions if you actually have a stiffness for that glue. The intent of the normal glue is to mesh different parts of the same body differently and glue them together. It's actually one part. It's just convenient to mesh them fine and coarse and even use different elements in different regions. While cohesive is specifically to model something like even simplified bolted connections, but that's a topic that we can spend a lot of time on, but rather something like a glued connection, actual glue, epoxy or whatever.
Okay. All right. Okay, now, thank you very much.
That's a pleasure. Any other questions? Okay, so thank you for attending. That then concludes the session for this week.